那如果说你这样做的话，那通常问题是什么？通常问题就是说你一旦加入这些新的 operator 之后，你是不是其实你又要回去再重新算一次？因为你现在 tree 了一个新的东西，对不对？那你这就担心你再重新算一次的时候，会不会造成在这边又出现新的 divergence， 又要 cancel？OK， 那如果新的 divergence 又 cancel 的话，又出来又不能 cancel 的话，那你是不是要再加上新的 operator？ 对不对？那你如果又加上新的 operator， 那你是不是又要再回来再算一次，就有新的 divergence？ 对，所以 the potential danger here is that if there's some ultraviolet divergence that is not cancelled by the tree factor, and you introduce a new operator, then you need to redo the calculation again, and then there might be new divergence that comes in, and then this becomes an infinite cycle. And then your Lagrangian just becomes more and more and more and more and more, all these new operators now coming out. And that becomes a problem, right? Because if you have all these operators coming out, remember, it's just, when we're doing canceling divergence is one thing, right? This is actually not what the Lagrangian is supposed to do. It's supposed to predict some physical observable. So again, that's the problem, right? We have all these operators coming out, and all the coefficients of these operators must be fixed by some renormalization condition, by some experimental data, right? So if this sequence does not end, then you're going to have infinite number of parameters to be fixed by infinite number of experiments, which renders the theory again useless in pure sense. Next lecture I'll let you know what pure sense means, but right now just accept that. We'll just take on the face value that when you have infinite number of operators, the theory is useless. Okay, you cannot do any prediction because you're always just doing experiments to fix the data. You're never ending experiments. Okay, there's no prediction to be done. Okay, so good. So we can have a flow chart, right? So you start out with the Lagrangian, and then you compute quantum correction. We compute loops. Then there's two possibilities. No divergence, or there is divergence. Okay. By the way, this is UV divergence. We're talking about UV divergence here. If there is UV divergence, then you ask two questions. If it's proportional, if it is proportional to the Lagrangian, or this is the tree level Lagrangian, and it is not proportional to the tree Lagrangian. If it's proportional to tree Lagrangian, that's fine. Then you just then we can just renormalize. Renormalize the coupling, meaning lambda off. If it's not, maybe I shouldn't have written it this side. If it's not proportional to Lagrangian, that means that it's proportional to some new operator, O nu. Then this means that you need to go back here and then add O nu. Okay? But obviously, so the danger here is that this cycle will not end. Right? You added O nu, then you need to, once you add an O nu, you need to compute the quantum corrections again, and then you again find ultraviolet divergence, which again is still not proportional even with this new O nu. Then you need to add another O nu, and then this might go infinite cycle. Okay? So if the cycle does not terminate, then we have a non-renormalized theory. whenever you hear non-renormalizable theories, this is what it means. It's a theory which has UV divergence, which is, when you first compute its UV divergence, it's not going to give you something that is absorbable by the original Lagrangian, which means it's going to have some new operator. And the new operator will modify it such that it still has ultraviolet, and again it's not proportional to it, and then the cycle doesn't terminate. Okay, and this kind of a famous example of this. Well, there's two famous examples. Well, there's many famous, but many of the Lagrangian are lost. But the most famous is GR. Okay, so general relativity, or the Einstein-Hilbert action, which start as square root of G R. This is a non-renormalizable theory. Okay, you start from the classical Lagrangian, you compute its one loop its quantum correction. You find that two loop order there's an ultraviolet divergence in 4 dimensions, and we requires a new operator. The new operator you add on generates another operator, and then just another, and it's infinite. Okay, so in principle, this is the problem with gravity. The real statement of why gravity is inconsistent with quantum mechanics is because the GR is a non-renormalizable theory. Okay, the quantum correction, in other words, the quantum corrections of GR doesn't make any sense. It renders, once you start considering quantum correction, it renders the theory useless. It's perfectly fine at classical level because you don't have to deal with any of this classical level, right? But once you start considering quantum corrections, the theory is actually a useless theory at the quantum level. Okay, of course, useless has the different 50 shades of useless. There's different degrees of uselessness, and we'll talk about what that actually means in terms of effective field theory in the later part of the course. Okay, good. So let me just talk a little bit. Let me just give me. I know all of you are tired at this point, but let me just tell you a little bit more, and then we'll delve into the detail in the next lecture. About what? About how to determine if the cycle terminates or not. Right? We would like to know if we can start out with the theory, and can we determine whether or not the theory is renormalizable or not. Now, of course, you would expect that I will not tell you that you have to compute all the ultraviolet divergence, right? 你一定可以猜想，我不会告诉你们说你们要把每一个圈都算出来，然后我们都去看它的 divergence 是多少，然后是不是能够 match， 一定有更好的方法去 determine 它，对不对？对 ，OK， so 我们现在讨论说到底怎么去 determine 一个 theory 是不是 non-renormalizable。那我们再回来看这个 flow chart。OK， 所以 non-renormalizable 的意思是什么意思？是不是意思说你有一个 operator 在这边，这个 operator 会 induce 加回 Lagrangian 就会 induce 一个新的 operator，and so on and so forth， 对不对？所以第一件事情是什么？第一件事情就是说，假如说如果说你一个 theory 是 non-renormalizable 的话，那这些 operator 总是要存在嘛？对，你在这 Lagrangian 上可以加的 operator 要存在，对不对？那所以说什么意思要存在？我的意思说，假设说你的 theory 有某些 symmetry， 那你或许你的 symmetry 大到说你只能写下某些 operator， 就写不下去，对不对？那如果你只能写下有限的 operator under 你所 develop 出来的 symmetry 的话，那这 theory 就一定会 terminate 啊，因为它没有其他 operator 可以产生的嘛。对，我们不要从你懂我意思吗？如果说这个 theory 是个 infinite 如果这个 infinite 的 cycle， 它其实在 imply 一件事情是什么？它 imply 说有 infinite number of operators 是 respect 你的 symmetry， 对不对？你的 theory 的 symmetry。Of course， 我现在在讲的是 provided that 我的 quantum correction 不会 break 我的 symmetry。OK， 所以我们假设说我们先 assume 说我们的 quantum correction 不会 break symmetry 的话，那 the fact that 一个 theory 如果是 infinite number of operator 的话，有 infinite number of infinite 是 non-renormalizable 的话，就 imply 了有 infinite number of operator 要一直加在你的 Lagrangian 嘛，就代表说你的 symmetry 必须要容许 infinite number of operators。大家可以接受这个 statement 吗？这是为什么 in some sense 为什么我们那么喜欢 symmetry？OK， 因为如果你 symmetry 够多的话，你可以开始把这条路掐死。因为你 symmetry 够多，你可以容许写下 operator 就不够，就越来越少。然后以至于说你 一开始就不可能会有 infinite number， 或许你 symmetry 够大的话，能够让它一开始就不会有这些 infinite number of operator 出现。OK， 但是 unfortunately for all symmetries， 你永远都会有 infinite number of operator。OK， 比如说什么意思？比如说，假设说你有 gauge symmetry 好了，我们就假设说 U1 好了。So， 我们想要讲的是什么 ？So how to get a renormalizable theory？ So we have the first proposal. Infinite number of operators simply do not exist due to symmetries. Okay, the proposal is that if you start out with a theory which has sufficient number of symmetry, then the available operators that you can write down that satisfy this symmetry might be finite. And since it's a finite, then this automatically kills this infinite cycle, right? Because each time you have to generate a new operator, but there are just not enough operators for you to generate. So it cannot be an infinite cycle. This would be a straightforward proposal to kill. Yes?
那如果说我把所有的 operator 满足 symmetry 都写下来，结果最后还是没有办法把那个 divergent cancel 掉，
这是 logically inconsistent 的，这没有这逻辑，这就没有逻辑，不是没有逻辑，这个逻辑就是 self contradictory 的。不过你 point 到了一个，OK， 我先是 make that statement， 你的逻辑这个逻辑是 inconsistent， 你们同意这个逻辑是 inconsistent。他问的问题是什么？他问的是说，假设说你现在把你的所有的 operator 写下来，然后它是 finite 的，你满足这个 symmetry 的 operator 是 finite 的，那但是它还是没办法被吸收掉。我 claim 说这个 statement 是不合逻辑的，你们同意吗？因为你如果你没办法被吸收掉，就代表你产生了一个新的 operator 啊，对吧？那这不是就是 self contradictory 的。你说你的 operator 是 finite set 的，这个 statement 就是 self contradictory。大家 follow 吗？我刚讲嘛，你今天这个 n， 我们现在先想要把这 infinite cycle 的这个东西 remove 掉。那这 infinite cycle 的这个东西 remove 掉的话，我们这 infinite cycle 的存在要求的是什么？是不是要求你有 infinite 的 operator 可以一直加，对不对？大家同意吗？你这 infinite cycle 先决条件就是 infinite 的 operator 要能够一直存在。所以我就 propose 说，是不是我可以 assume 说你的 theory 有某些 symmetry such that infinite 的 operator 不存在，你只有 finite set of operator 去 respect 这个 symmetry。这是一种方式可以把这个掐掉，让你一开始就知道你如果说这样的话就很赞嘛，你只要 assume 说你的 nature 有这个 respect 这个 symmetry 的话，那你就有个非常 predictive 的 Lagrangian， 对吧？可是通常但是问题出在什么？问题出在说我目前没有找到这种 symmetry。最简单的，你们会讲说 gauge symmetry， 这是个很 strong 的 symmetry， 对不对？所以我们看 gauge invariant 的 operator 会是什么？所以比如说，假设说 example 啊，比如 gauge symmetry， 所以我们知道，比如说我们就讲了 abelian 的 gauge symmetry， 我们先讲 abelian 好了。那我们知道 f mu nu 是不是一个 gauge invariant 的东西？对不对？那当然，我们要 maintain Lorentz symmetry 和 Lorentz invariance 嘛，所以一个 Lorentz invariant operator 就是 f square 是 Lorentz invariant。所以 example， so let's assume we have gauge symmetry. So if we have gauge symmetry, then that means that for gauge field you need to write everything in terms of field strength, that means so that is gauge invariant, right? But then Lorentz invariance, so Lorentz invariance tells you that everything has to be written in terms of f squared, because that's the Lorentz invariant object, right? But then this means that any function of f squared satisfies both of these. Right? So you can write down infinite number of operators. Right? You can write down f squared, f4, f6, whatever, right? There's infinite number of them you can write down. They're all gauge invariant and perfectly fine. Okay, again, we're assuming that the quantum corrections preserve all the symmetries of the theory. So, of course, as you probably know already, that in the middle of the course we're going to talk that actually there's cases where quantum corrections break the symmetry. But just assume symmetries. Generically, any symmetry you think of, we can in principle write down an infinite number of terms that satisfy that symmetry. Okay. Of course, there may still be out there unknown symmetry that we haven't found yet. For example, nonlinear symmetry, so that can constrain the number of operators, and this we will talk about at the end of the semester. But for the bread and butter, the usual vanilla symmetries that we all know of, that you should be familiar with, it doesn't do this. Okay, so this does not happen. This proposal doesn't happen. There's no symmetry that we know of that can kill this cycle. Okay. But actually writing this, we know that, for example, for QED, we know that actually when we write this out, QED only has f squared. It doesn't have all of these. Right? So, maybe you can ask, is there other reason why these things will not appear? And so we'll start with the second proposal next time. Okay? And the second proposal was the proposal 2, let me just write it out. Interactions only involve marginal operator. And what does marginal operators mean? It means that we talked about this before, right? I'll give a brief review next time. Marginal operators means that the coupling constant is dimensionless. Okay. If your theory involves interaction that only has dimensionless coupling, maybe this will help. Now you might ask, why would this help at all? Remember a very crucial point. What are we trying to do? The reason that you have all these new operators is because it's coming from some UV divergence, right? Right? If it's coming from UV divergence, then it's coming from some loop computation, right? What are loop computations? So this is just a 5-minute preview, and so if you don't follow what I'm saying, that's fine, because I'll talk about the details in the next second. Remember, what are we doing? We're computing some amplitude, for example, as a function of kinematic invariance, as an expansion in terms of our renormalized coupling, right? That Ci is going to be some function of p squared, some function of s. All right? And we have an infinite expansion in principle, right? And what was our problem? Our problem was that the Cs here has a divergence that needs to be absorbed, that needs to be canceled. That's our problem, right? Now, in order for this new operator to appear, right, it has to appear from the divergence of this computation, right? Good. So now, if lambda r has no dimension, then this series is a very interesting series, because if lambda r has no dimension, that means all of these coefficients to arbitrary lambda r, they all have the same dimension, right? They all have, it's just because lambda r has the same. If lambda r have dimension, then each one of these functions will have different dimensions, right? But if lambda r has 0 dimension, which means that it's a marginal coupling, then this is a marginal coupling constant, then all of these functions have the same mass dimension, right? Why is that so good? If everything is the same mass dimension, that means that all of these kinematic invariants is going to have the same dimension as your original classical Lagrangian, right? that means that whatever the ultraviolet divergence happens in here must have the same dimension as the operator that appear in your tree Lagrangian. So we can look at QED, right? So remember we have F squared, we can have FQ, F4, so on and so forth. What's different between, what's special about these other operators is these operators have different mass dimension than the original tree one. Right? It has more derivatives. Right? So, if you have marginal coupling, since the divergence are appearing in these quantum corrections, the dimension of this quantum correction must have the same dimension as your tree. Then these operators cannot appear. Everybody follows what I'm saying? And so, if you have marginal coupling, then you automatically truncate a huge swash of operators, because usually the operators that you write down have more and more dimensions, right? Because you have more and more fields. But because if you're restricting yourself to just marginal coupling, then the marginal couplings imply that the loop corrections will all have the same dimension as the tree coupling or the classical Lagrangian. Then once you write down the classical Lagrangian, no matter how many loops, you don't have to do any computation. You know that even if there's a divergence, it's always going to have the same form as an operator has the same form as a tree, and therefore your theory is renormalizable. Okay, and for us, the standard model is of this form. Okay, the standard model is a Lagrangian where all the coupling are all marginal couplings. Of course, there's relevant coupling, but we'll talk about that more. But relevant couplings are not a problem. But essentially, but most of the couplings are all marginal. There's no irrelevant coupling. There's nothing that will generate the higher dimension operators. And this is also what's wrong with gravity. Okay, because gravity is a theory where the coupling constant is the Newton constant, and it's a dimensionful parameter. So it's not a marginal coupling, and that's why we're sure that gravity will be non-renormalizable because it's just because that it has an infinite cycle. You can actually write down all these generators, all these operators, and these operators in principle should appear in the loop corrections. Okay. All right. So next lecture, I'm going to go into more detail about this discussion and this argument. I will give you some more examples, and then of course this whole argument relies on the fact that the symmetries are not broken, right? Because I mean these operators satisfy gauge symmetry and so forth, right? So now we're gonna start looking at whether or not in which ways symmetries can be broken by quantum correction. So because that's also going to have relevance for whether or not the theory is normalizable or not. Okay. So this is basically the thing that we'll talk about in the next lecture, and also we're going to talk a little bit about the renormalization group flow. But as you see, all the discussion here is just scalar field theory, right? But it already captures the different aspects, all the aspects of quantum field theory. So then Henry will come in after the next lecture is mine, and afterwards Henry will come in and start to do the exact same thing, but with fermions. Okay, so we'll start doing things with fermions in the loop. And the reason that you can say, oh, fermion is just detail. Why do we care about fermion? There's new aspects of fermions when fermions involved, and the new aspect is precisely the breaking of quantum symmetries. Fermion can start breaking. Chiral fermions will start breaking gauge symmetry, and so you probably heard about chiral anomalies before. And so those are only when fermion appears will this happen. And we'll talk about that in Henry's lecture. Okay, so this is the near future plan for this course. Okay, all right. So let's